students, I am Tulika Banerjee. Today I bring you the next learning episode in BSc Forensic Science on an important unit of the paper titled Fingerprints, that is Chemical Method for Detection of Latent Fingerprints, Part 2nd, Ninhydrin Method. In this lecture, you will be studying about the significance of Ninhydrin method of fingerprint detection and also the chemical and physical parameters involved when Ninhydrin is being used as a fingerprint detection reagent. In addition, you will be studying about the post-treatment and pre-treatment procedures which enhances the quality of Ninhydrin developed fingerprints. We will wind up this lecture with the conclusion. So, let's start our today's lecture with a brief look at the modules which we will be learning today. First is Ninhydrin method for detection of latent fingerprints. Next, preparation and properties of Ninhydrin. Then third, we have Ninhydrin as a fingerprint reagent. Fourth module is of post-treatment of developed fingerprints. Module fifth is for pre-treatment of developed fingerprints, and lastly we have the conclusion. So, let's begin with the first module of this lecture, that is Ninhydrin method for detection of latent fingerprints. A latent fingerprint is formed when the sweat pores of the papillary ridges leave a deposit of perspiration on a surface with which the finger has been brought into contact. Human skin possesses three types of sweat glands. Eccrine glands are widely distributed throughout the body and are particularly numerous on the palms of the hands and the soles of the feet. Besides the water content, eccrine sweat contains up to 1% of other substances, of which about 1/2 are inorganic ions. The remaining half consist of organic derivatives like urea, sugars, lactic acid, fatty acids and amino acids or proteins. The amino acid content of sweat residue may be fixed by treating the latent fingerprint with a solution of Ninhydrin reagent. The amino acid Ninhydrin reaction produces a purple compound called Rehmann's purple, which gets deposited along the ridges, making the latent prints visible. Ninhydrin is particularly useful for developing fingerprints on porous and absorbent surfaces like paper, paper products and cardboard and wood, whereas the inorganic ions and most of the organic ingredients of sweat deposit tend to interact with the cellulose content of paper or wood. The amino acids remain inert. Moreover, with passage of time, the amino acids do not migrate within the capillaries of the substrate. Therefore, the Ninhydrin method makes it possible to develop fingerprints that are many years old. Next, we will be studying about the preparation and properties of Ninhydrin. Ninhydrin was synthesized by Rehmann in 1910 in an attempt to oxidize 1-hydrindone to 1,2-diketohydrindine. However, a di-substituted hydrindone was obtained, which was subsequently hydrolyzed to Ninhydrin. Ninhydrin crystallizes as pale yellow prisms from ethanol solution. On heating, in the solid state, it changes to pink or red color at 125 to 130 degrees centigrade, becomes deep purple at 130 to 140 degrees Celsius and finally melts with decomposition at 241 degrees centigrade. When exposed to sunlight, Ninhydrin turns red in color. Therefore, it is stored in a cool, dark place. Normally, organic compounds having two hydroxyl groups on the same carbon are unstable. However, Ninhydrin is stable. It owes its stability to intramolecular hydrogen bonding as shown in the structure on your screen. When heated in vacuum or when treated with thionyl chloride, Ninhydrin dehydrates to 1,2,3 indane trione. Compounds such as as shown on your screen, having a vicinal triketonic function are also useful for developing fingerprints, although the results are not as good as that of Ninhydrin. The most useful reaction of Ninhydrin is with amino acids. A purple colored compound is formed as a result of this reaction. The product is called as Dermatoglyphics purple or RP, as shown on the screen. The reaction between Ninhydrin and a representative amino acid is displayed in the figure. The amino acid Ninhydrin reaction has proved to be useful in several analytical procedures. Incidentally, this very reaction makes Ninhydrin a reagent for fingerprint development. Now we will be studying about Ninhydrin as a fingerprint reagent. Ninhydrin was first used as a fingerprint reagent in the year 1954 when two Swedish scientists S. Odin and von B. Hofsten developed latent imprints on paper, cardboard and similar material with its aid. A year later, Odin patented the procedure. Broadly, the procedure for developing latent finger marks involves spraying the Ninhydrin solution on the surface containing the impression from a distance of about 6 inches. After the solvent evaporates, the solution is re-sprayed. The surface is then heated for a short time without allowing it to come into contact with the heat source. If quick development is not required, the item may be allowed to dry at room temperature. Better results are obtained by natural drying. A sample fingerprint developed by Ninhydrin method has been shown on your screen. During experimentation, there are several parameters that need to be adjusted for adequate and satisfactory development of fingerprints. There are chemical parameters such as the concentration of Ninhydrin, the nature of solvent and the acidity of the formulation, as well as physical parameters such as the mode of application, heating temperatures and relative humidity. So first here we will be discussing about the chemical parameters. Concentrations of Ninhydrin varying from 0.2 to 1.5% have been found suitable for fingerprint development. Various types of solvents have been tried out for preparing Ninhydrin solutions. The reagent dissolves in most organic solvents such as methanol, ethanol, acetone, diethyl ether and naphtha. The choice of the solvent depends on whether the document is scripted or not. Most organic solvents tend to despoil the calligraphic script. Freon 113, also called fluorosol, proved to be the most remarkable solvent for dissolving Ninhydrin. It does not interact with ink. It is absolutely non-reactive and therefore there is no chance of the surface becoming degraded. It is non-toxic and therefore poses no occupational hazard to the user. Above all, it is non-flammable and therefore quite safe to use in a laboratory. As a result of this last characteristic, the freon-based composition has come to be referred to as non-flammable Ninhydrin or NFN. The NFN develops finger marks on a wide range of paper items. It provides a minimal amount of background effects. Moreover, it is effective on surface coated papers such as currency notes as well as the gummed side of postage stamps. It is, however, being feared that it may not be possible to continue with NFN in the years to come. Freon 113 belongs to a class of compounds called chlorofluorocarbons. These compounds are being banned out under the terms of Montreal Protocol on phasing out of ozone depleting substances. There is therefore a need for the suitable replacement of Freon 113. Petroleum ether provides an alternative as it too does not interact with ink. However, petroleum ether is highly inflammable and explosive in nature and is therefore considered hazardous. Supercritical carbon dioxide is being considered a possible substitute of Freon 113. Next, we will be taking here up the physical parameters. Ninhydrin is applied to the surface impinged with the latent fingerprints generally by spraying, swabbing or dipping. Of these, dipping operation is the most extensively used. However, fragile paper items such as paper napkins tear apart on dipping and therefore the spraying procedure is followed. Swabbing action tends to smear the ink and is therefore avoided on scripted documents. Less conventional methods include exposure to Ninhydrin fumes, dusting with Ninhydrin powder or placing a paper dipped in Ninhydrin solution over the fingerprint impression. If development time is not a consideration, Ninhydrin spray documents should be allowed to develop at room temperature. This may take a few days, but the results are excellent. Normally, however, the surface is heated to 80 degrees centigrade so as to accelerate the development process. The mode of heating is also important. Heating may be carried out by a steam iron. Better results are obtained if the iron is moved from 1 to 2 centimeters above the surface. Most forensic science laboratories have adopted this procedure. Others have shifted to microwave ovens for heating and steaming. In the absence of these equipments, the object may be waved over a flask containing boiling water. In either case, heating has to be carried out in a humid atmosphere. Optimum development of fingerprints occurs at a relative humidity of 65 to 80%. Modern fingerprint laboratories are endowed with Ninhydrin acceleration chambers. There is a provision to control temperature as well as to maintain humidity in these chambers. Paradoxically, if the developed prints are kept in humid atmosphere, they fade out at an accelerated pace. Light and heat are other factors which cause fading of imprints. When Ninhydrin developed prints are made fluorescent by post-treatment with zinc chloride, they fade out on exposure to sunlight or xenon arc light. In presence of moisture or high humidity, the fluorescent character is lost and so is the clarity of the prints. To extend their lifetimes, it is recommended that the Ninhydrin developed prints be stored in a dark place and at a low relative humidity. Next, we will be talking about the post-treatment of developed fingerprints. Although the Ninhydrin method is considered to be a standard procedure for developing latent fingerprints, it suffers from a number of demerits. The chemical reaction between Ninhydrin and the amino acid content of sweat deposit is quite slow and therefore the developing time is quite long. Many surfaces interact with Ninhydrin, giving a strong background coloration that masks the developed prints. Further, the concentration of amino acids in perspiration is quite low and hence the developed prints usually do not show a sharp contrast. Moreover, the method is not applicable to non-absorbent and dark surfaces. Lastly, on many items, the Ninhydrin developed prints tend to fade out within a very short span of time. In order to avoid these problems and to improve the working performance of Ninhydrin reagent, the procedure for fingerprint development may be modified. The modifications involve the conversion of non-fluorescent Rahman's purple deposited along the ridges into a fluorescent derivative by post-treatment of the developed prints with a suitable metal salt. The fluorescent deposition shows a marked enhancement in clarity and sharpness when illuminated by a light source. Then we have the post-treatment with metal salts in concert with arc lamps. Roehmann's purple, the reaction product of ninhydrin with amino acids, forms coordination compounds with many metals. The metal Roehmann's purple complexes are generally red or orange in color. Some of these are fluorescent in nature. This reaction may be used to overcome the contrast problem of ninhydrin developed prints as well as to improve the stability of finger marks. The reaction of Roehmann's purple with a group 12 metal salt like halides or nitrates of zinc, cadmium or mercury in an ethanol freon 113 solvent mixture produces a photoluminescent complex. However, invariably zinc chloride is the reagent of choice for post-treatment operations. After the solvents evaporate, the sample is dipped in liquid nitrogen so as to bring down the temperature to -200°C. When examined under an arc lamp, intense fluorescence is produced. A xenon lamp is the most common source for illuminating prints developed by ninhydrin and post-treated by zinc chloride. A Watkins indium lamp, a Kent's quasar lamp or a unilight lamp may also be used for illuminating the finger marks. This procedure offers several advantages. The post-treatment may be carried out only when it is deemed essential if a sufficient degree of contrast is produced with ninhydrin alone. The subsequent steps may be avoided. No expensive equipment like a laser is required. Further, prints may be photographed using conventional fingerprint cameras also. Then we have the post-treatment with metal salts in concert with lasers. The arc lamp induced fluorescence is no doubt a cost-effective method for developing latent fingerprints. It suffers from a demerit. The fact that the post-treatment has to be carried out at -200°C rules out the examination of larger exhibits removed from the scene of crime, as it is difficult and impractical to store cryogenic nitrogen in big tanks. The problem may be obviated by substituting the conventional arc lamp by sophisticated laser equipment. With lasers, there is no need to plunge the sample into liquid nitrogen, except in cases requiring special handling. Moreover, the ridge deposit produces a stronger fluorescence with a laser than with an arc lamp. Laser excitation enables detection of very old prints after these have been developed with ninhydrin and post-treated with zinc chloride. Fingerprints developed by ninhydrin zinc chloride method become highly fluorescent under the argon laser light. The 480 nanometers line of argon laser is appropriate for excitation of the orange zinc Roehmann's purple complex that absorbs at 485 nanometers and emits at 560 nanometers. Further, with zinc chloride post-treatment and argon laser examination, the ninhydrin method may be extended to the detection of latent fingerprints on non-porous surfaces like glass and stainless steel. The complexes formed by combination of Roehmann's purple with europium or terbium salts too have been found suitable for fingerprint development, particularly if the background surface of the evidence is fluorescent in nature. These complexes show enhancement of the lanthanide luminescence via intramolecular energy transfer. Moreover, the lifetime of the luminescence is much longer than of the usual background fluorescence. The lanthanide complexes are therefore suitable for time-resolved luminescence imaging. There are a few disadvantages associated with lasers. The casework has to be carried out at the Fingerprint Bureau. Portable lasers which may be carried to the scene of crime are not yet available. Laser equipment is quite costly. When optical spectroscopic techniques are used in combination with lasers, the operational procedures become tedious and complex. However, the end results obtained with lasers are so remarkable that one becomes inclined to believe that their merits outweigh the demerits. Next, we will be studying about the pre-treatment of developed fingerprints. The amino acid content of sweat deposition is quite small and therefore rich details are often not visualized clearly with Ninhydrin, even after post-treatment with zinc chloride and laser examination. To improve the sharpness of the developed prints, pre-treatment with hydrolytic enzymes like trypsin may be tried. These enzymes hydrolyze the protein content of perspiration to amino acids, thereby increasing the chances for enhancement of developed fingerprints. The hydrolysis reaction has been shown on your screen. Initial attempts to pre-treat the fingerprint samples proved futile because the enzymes were dissolved in non-aqueous solvents in which they denatured. Subsequently, however, the dusting of powdered enzymes before the Ninhydrin treatment was tried. This gave pronounced enhancement of latent finger marks, especially those that were 2 weeks to 3 months old. The methodology involves the following steps. The enzyme is applied by dusting over the finger mark and the sample is incubated for about 40 minutes at 35 to 40 degrees centigrade under a relative humidity of 80 to 90%. The article is then dried and excess enzyme is blown off. This is necessary since the enzymes to react with Ninhydrin, giving colored compounds. The dried enzyme-free sample is treated with Ninhydrin and re-incubated for about 18 hours. If rich details are still not clear, further treatment with zinc chloride followed by laser examination may be carried out. Enzyme pretreatment method cannot be applied to routine samples. It requires a long developing time. It is unsuitable for field work. The technique may be tried out over articles bearing extremely weak fingerprints. Now, dear students, let us conclude this lecture. Ninhydrin is one of the most suitable reagent for revealing latent fingerprints on absorbent surface like paper, cardboard, raw wood and plasterboard. It is effective in visualizing both the fresh and the old prints. Its handling requires only a meager degree of skill and experience. It poses no occupational hazards, provided some simple safety precautions like using gloves, splash-proof goggles and fume cupboard are observed. Ninhydrin is a versatile reagent in the sense that its formulations are amenable to modifications. Results may be improved by changing the concentration, solvent, heating temperature, heating mode or by pre-treatment of imprints. Enhancement may also be achieved by post-treatment of developed prints by metal salts in combination with arc light or better still with lasers. Even if this methodology fails, there is always the option of using a Ninhydrin analog for fingerprint development. It is therefore not surprising that Ninhydrin has been nicknamed as the latent print examiner's chemical workhorse. With all these information, here we come to the end of today's lecture. Do keep in mind what we have discussed today. I'll be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I'll see you in the next lecture. Have a great day.